How are things actually implemented behind the scenes? Well, it's a very well-known paradigm, and you actually done that in lab number 2, and it actually uses the runtime stack. Let me just go back in history around 60 plus years around and discuss what was, and then when we see what is, we'll see the major difference between the two. So let's go back and ask ourselves what was. Now, the way the computers used to work is that we had a code segment. We still do. So we had a code segment where all the code was, and then we had the data segment. And inside the data segment, the system used to pre-allocate all the data that it needed. So for example, we had 3 functions. It's the function main, the function A, and the function B. So all the data that each one of them needed was already pre-allocated. Now, when you called the function, the compiler already knew where that data will be, right? If you needed some variable C inside A, so there the compiler already knew that there it was, and it would just put into the code, where it should look for that data. And this is the way computers used to function until somebody came up with a smart idea. Why don't we just go and create a runtime stack? And what we do on the runtime stack is every time we enter a scope, every time we enter a new, function, we go and we put on the runtime stack a what's known as an activation record instance of the function that we're actually using. For example, let's say main. And in that activation record instance, you would have all the variables in main and stuff. And then let's say for main, we go into A. So you would have an activation record instance for A. And you can have another one again for A again. Notice again, here's A again. And you can have A again. And you could have a B, and then you could have a C, and whatever it is. Notice there's no limit on how many times you can call the same piece of code. And this was actually a super invention. You can read up on the paper in the Moodle by Dijkstra, the famous guy, the famous Dijkstra, about the runtime stack, where it's actually, they proposed this idea of using a runtime stack in order to deal with the data. And we're getting automatic data. Notice this. This is not static data. This is static data. And here we're getting automatic data. And then we have to deal with all kinds of things like, well, so where in the runtime stack is the C that I'm looking for, right? The same C. So we have a C over here. We have another C over here. We have another C over here. They're all the same C. They're all, it's all C, but it's different C's. So which one are actually dealing with right now? Which one do we want? And all the things using the base pointer, the offsets, and everything we learned to know and love back from the lab number 2 and other places that we've seen it, in compilers and operating systems and other places that we've seen the actual uses of all these registers and all these pointers and stuff. So we're actually getting an automatic functioning of this activation record instance. As a side effect of not using the static mode, but the automatic mode, notice that we're getting a very interesting use, recursion. Notice that until the point when we went and we actually used until the point where we actually went and we allowed functions to have themselves instantiated a couple of times, there was no recursion. If you take a look at the static version that used to be, you cannot run A twice at the same time. It's one or the other, right? It's one or the other. But if you go and you have this actual runtime stack, we're actually getting a side advantage known as recursion. So anyway, this runtime stack is actually what's running the system behind the scenes right now. It's actually very, very similar to what you guys did in lab number 2. And therefore, there's no reason for me to actually expand too much on this kind of topic.